Okay. Okay. Last week we we have learned at least the product rule, the quotient rule, and the introduction to these derivatives of trigonometric functions. Okay. And I think we can start with the sine x, right? And if we just look on the graph itself, when we derive and take the slope, we know that the derivative of the sine will be cosine. Okay, and I give you the idea of if we try to look on the limit definition to our derivative, and we see that we have the cosine x as the result. Okay. Now, if we look at the graphs of, let's say this is the cosine, right? The cosine. If we try to take derivative one more time, okay, so it's going to be positive here, negative here, so it's going to be like this, right? Right? Okay. So if you compare with the first one, then it's perfectly the opposite sides of sine, right? So we could say that if we have f prime cosine x, then if we take one more derivative, it will be minus sine, okay? So you write that. So if we take the second derivative, it will be negative sine x, okay? So uh, let me write the summary for you. So if we have f of x is sine x, then we have f prime x is cosine x. And if we have f of x is cosine x, then the derivative is negative sine x. Okay. Okay. The interesting point on the sine and cosine is they always have sine, cosine, sine, cosine. They have the pattern. Okay, they have the pattern. The difference is sometimes they will have the negative. When they have cosine, we need to multiply with the negative. Okay, so imagine if you have uh, or let me put this way. Okay, let's try to derive this maybe 5 times or 6 times. Okay, let's see how it looks like. So if we take the second derivative, this will be negative sine x. Okay. If we take the third one, what will be? It will be negative cosine x, right? If we take 4 times, it will be sine, right? So after 4 times, we go back to the original equation, which means if you take derivative, let's say 1,000 times, you do not need to derive 1,000 times. You can see that every 4 times it will get sine x. So you can think that every 4 times is 1,000 is to 250, right? So it goes back to the sine x, okay? Or if you take some, let's say 24 is still 4, right? It still get a factor of 4. So maybe 25. So 25 probably going back to cosine. Okay? 26 going here. Okay, got the idea. So you can see the pattern, and when you have some numbers of repetitions for derivatives, you could think that every 4 times it's going back to the original functions. Okay, so it's actually a good way to think. Okay, because I think in your textbook there is a question, if you derive maybe 30 times, 31 times. Okay, you can think from the pattern. Okay, you can think from the pattern. And sometimes the question is not it's not just like plain as this one. Maybe it has something to do with the, maybe it has sign maybe x squared, and then you will see also a pattern that the x squared will going to be derived, and you can see the product rule also can be applied. Okay, so whenever you see any sine or cosine and you have to repeat derivatives many times, the clue is the hint that you are going to apply is to see the pattern. Okay, to see the pattern. Okay. Okay. Aside from the sine and cosine, another trigonometric functions that uh, essentials at least is a tangent, right? Sine, cosine, and tangent. At least these three is important in trigonometry. So let's start with the tangent. So let's say we have the tangent. Okay. Well, to start the tangent, we can think the tangent from sine over cosine. Okay, we can think from that way. So we can say that this is sine x over cosine x. Okay. Okay. Now we have this rational form. Now, if we want to take derivative, then we know how to take the quotient rule, right? So I think we can just stick by the quotient rule and try to derive sine over cosine. Okay. Let me write here to make it clear. So let me give you the the formula here to make you familiar with the equations. So we will have cos squared x plus sine squared x. Okay. By the identity, this will be 1. Okay. This will be 1, the result. So this will be 1 over cosine squared x. Or you can say it's secant squared x. Okay. So we've done the sine, cosine, the tangent. Okay. So let me write the summary down here. So sine x, this become cosine. The same thing if you have the secant. If you have the secant, let's write maybe here. And let's say gx is secant. Well, we can start from the statement that the secant is 1 over cos sine x. Okay, and uh, well, we could use the quotient rule or just a normal power rule. That's okay. But let's just stick with the quotient rule. So this is going to be cos squared x, and let me write f g. So this left is 0 minus uh, minus sine x. So it's going to be sine x over cos squared x, or sine x over cos x, or we could say this one becomes secant, this one becomes tangent. So we have secant x tangent x. Okay, so let me write and rearrange this part. Okay, so if you have secant x, okay, you could also do similar structure with the cosecant, okay, the cotangent also. But I think if you manage to master at least this four, it should be enough. Should be sufficient. Okay? Whenever you maybe not really sure what is the result, you can try to do the quotient rule. Okay? So I think uh, for today, we finished this trigonometric. Okay? The next sections that I'm planning to finish off by today is the chain rule and implicit differentiations. Okay, so at least I will give you more concepts for today, and maybe tomorrow we can review. Okay, we can review. Okay, so this is I think the necessary derivative for trigonometric. Okay. Okay. Uh, okay. I hope everyone finished their notes. Okay. Let me take the new page. We start with the chain rule. Okay, so to begin the chain rule, okay, uh, let's assume let we take let's say this capital F. Okay, this is a combination function. So let's say it has F and combined with G. We would like to know, okay, what is the derivative of this capital F? Okay, when we know that this capital F is this composite or combination function. So we start with the definition of this composite function. We know that this defined as F and then G, which means that we have a function G inside a function. Okay. Now the idea of the chain rules come from here, in which we are going to take derivative on this capital F. Okay. If this is only one function, we know that we have the derivative, right? We have the derivative. But if a function inside the function, what will be the derivative? Okay. So I will give you the definition first, and maybe take some time to prove. Okay. Maybe the definition first. So if G is differentiable, let me write this, differentiable at x, and F is differentiable at G of x, then composite F defined by F is differentiable at x, and the F prime, let's say F prime x is equal F prime of gx multiplied with the G prime x. Okay, this is the first definition. Another way, we can write in Leibniz notation. So in Leibniz notation, if y equal function of, let's say, u is dummy variable, and u is a function of x, function g, they both differentiable, then we could write dy dx equal dy du and multiply with du dx. Okay. This is just illustrations. If you have a function inside the function, or if you see that you can make up the function y, and then you have another dummy variable u, and then you want to make or connecting this y with the x. X is independent variable, so you are usually we derive with respect to x, right? So that means we are taking this x as our independent variable, our single variable to be derived. Okay? So we take that as dy over dx. Okay. Now the easy way to understand the chain rule, I think, from this equation here, what chain means, you are chaining your dummy variable here to get through your objective or your goal, which is dy over dx. Okay. So you can have a lot of dummy variables. So you can have maybe du here, and maybe if you want to make maybe dv, dw, w, okay, and you have dz, and then dx at the end. So you can have many dummy variables, which means you can have many functions in your composite. Okay. So not only like one function inside a function, so you can have many functions, like inside a function, inside a function, inside a function, and you can have many chain rules. So that's how you get the chain. The chain means you can chaining this all this dummy variable together. Okay, that's how the chain rule works. Okay, so to give you the idea, okay, let me give you maybe example first. We have learned this trigonometric. So if we have, for example, let's say we have a functions sine, and then we have x squared here. Okay. So we have sine and we have x squared inside this sine. Okay. We can think this as a composite. The big function is sine x, and we are going to have the x squared inside the sine x, right? How to write this is basically we are going to derive the whole part here. The we sometimes I call this outside functions. Okay. Outside function. And this little part here is the inside function. And this inside function, it can have more and more functions. This is just an example. Just maybe the outside function is just sine x, and the inside function is the x squared. Okay. The way you treat this functions when you derive, we take the outside functions, derive, and then multiply with the derivative of the inside function. Okay. That's I think the way you look at. Okay. So we take this as first derive the sine is become cosine, and write exactly the same thing, and then multiply with the inside function, which is 2x. Or you can write 2x cosine x squared. Okay. Now what if we have a different function? Let me give you on the right side here. It's sine x, but it has squared. So I'm reversing the functions. Okay, so now it's sine x inside of a bracket and then squared. It's composed of the same function as the left one, but we reverse it. Okay. So we have the sine x now inside x squared, right? Inside x squared. Okay. So now the outside function is this bracket squared. Okay. So let me write. So this is the outside function. Let me write this is sine x. This is x squared. And this is x squared. And this is inside. Okay, now if we take the derivative, Now we start with the outside function, which is the x squared. Okay. If you maybe feel not comfortable doing this derivative at the first time, my suggestions, we can start with just x squared. Okay, imagine this is x squared. We derive becomes 2x. Okay, and then sine x derived becomes cosine x. Okay, so 2x we can change x to the original function. So 2 sine x and then multiply with the cos x. Or if we write here, then this will be 2 sine x multiply. Or let me write uh, one by one. So d dx of sine x. Or we can write 2 sine x cosine x. Actually, the same thing here. We can write, let me write here and make d dx of the x squared. So the first part here is the general, the outside function or the general function here. And this part will be the inside function. Okay. There is a proof, how to prove that our chain rule definition is correct and makes sense. But I think I will skip that in class. I will give you as additional notes. Okay? I think that will be better, so we can have much more practice and exercise in class, I think. Okay. And also, if you have tried my exercise, okay, if you try, I think by today, aside from this recording, the class recording, I will also give you the solutions for the exercise. I will give you video solutions. Okay? I think 2 or 3 questions, I think a little bit difficult. Uh, do you agree? Have you tried? Have you tried my exercise? Yeah. Which one you think difficult? This one? Okay, yeah, yeah, I agree because I take from somewhere else, not from the textbook. Yeah, I will give the video explanation, and also because I give you exercise on the limit, perhaps around this Thursday or Friday, I will post about the quiz, the link, so you can try to check, and then maybe finish by 4. I think 4 days should be in the 4 to 5 days. So you can choose which day you are going to work on. I'm going to use a different platform, not the quizzes, so different platform. Um, but the idea on that platform, uh, you need to use my suggestion, not just regular browser, but if you have uh, the using Chrome, you need sometimes you need to use the incognito mode, or if you use different browser, you need to use the private browser because it has something to do with the coding the so the to load the picture and then the font. Sometimes some laptops not really compatible. But if you know how and you can clear your cache file, or yeah, if you use Windows laptop, sometimes you need to um, erase your history cache files so you can open the link. I will put all the procedure. So if you have any difficulty, you can just message me through Moodle or just email me. Okay. Okay. So I will try um, to get on the chain rule again. So let's try one more here. Example. Let's say we have h. Uh, Okay, let's try with this. And then another one. Let's make another f. Let's try a little bit complicated. Okay. Okay, so the first one, I think it should be quite easy. So we can imagine that this will be the outside and this will be the inside. So you could take 5 and multiply with -6, or we can have -30. Okay. The second one. How about the second one here? Anyone try? Okay. How about you? Okay. Okay. Yeah. Okay. Oh yeah, and then your question is supposed to be in the indeterminate form. So we are going to use the L'Hopital rule to solve the one we have limit before. Yeah, it's the I think next two chapters. So this is the we can say the outside function is square root of x, right? And the inside function is this, okay, which has another square root of x. Okay. So we can start from, uh, maybe let's take down here. Start from taking the square root of x as 1 over 2 square root x plus square root of x. And then, well, we can take times and progress slowly. And then the inside is x plus square root of x, like that. Okay. So we could take, oh, let's become curvy. Okay. X plus square root of x, and then this ddx becomes 1 plus another. Okay. You can stop here because the question is not asking where you need to stop. So I think you can stop here, unless maybe the question gives you some options that maybe rewrite in different form, and then you need to match with those forms. Okay. So, but I think we can stop here. Okay. So if you have any questions in your textbook or in exam, it's not really giving any specific form. You can stop anywhere. Okay. Hmm? The left part, maybe like here, right? Okay. 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 Maybe questions. If you're not familiar yet with this square root, let me write something on the left. That if you have square root of x, if you take the derivative, this will be 1 over 2 squared of x. Okay. You can prove this with the power rule, x with power of half, and you can see that if you derive that, it will have this. Okay. Okay. And I think more examples will be tomorrow. Okay, for this one. This is just a um, introduction for the chain rule. Okay. Maybe a questions you need to maybe think uh, after the class. How about if we have, okay, let's say we have the, um, let me give you a little really long x plus x plus plus and going infinitely. Okay. It seems really long, impossible. But after we learn the logarithmic derivatives, and yeah, I think after that we can at least try to find out if we want to derive this. Okay. But later, okay, later. This is just if you want to try to think, okay. Maybe try thinking from here, okay, from here, and then you add one more x, and then try to derive and add more x, and let's see what kind of derivative results you have. Okay, so if you have this infinite point of x, x plus square root of x, and then plus 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 plus. Okay. Okay. We will go back here later. Okay. If I forgot, please remind me. Go back to here. Okay. But after we learn the logarithmic, okay? The logarithmic derivatives. Okay, by the way, I think when we deal with the exponent, I forgot to mention how the, um, let's say we have the b, um, let's say the f of x is, okay, or let me write with y. We can rewrite the b with power of x in terms of e and then power of l and b. That's going to be b and then x, like that. This e with power of l and b is b, okay, and y is b power of x, okay. So what we are going to do is we try to derive this b with power of x, which means we are going to derive this e. So as you remember, we could have the e, l, and b x, and then we derive the inside functions l and b x, right? L and b is just a constant, okay? So we could just say the derivative of l and b x is just l and b. So this is going to be e multiplied with l and b. And this is going back to the original equation, which is the p with power of x, and then l and b. So that's how we can also get through the exponent through the chain rule. Okay, the chain rule. Yeah, maybe you can also, if you're not familiar with the ln, if you powering e with ln, it means it's actually the one uh, that, so basically e and ln will cancel each other. Okay. Well, you can go back to learn the log. Okay. I think for um, the logarithmic in basic of math class, we also will going to learn more details. So I will going to give you some notes on the log. Okay, maybe I will take example on the right side here, just to take notes. Um, if you have 5 with power of sine x, what will be the derivative? So you have 5 with power of sine. Okay. So if you see the consistency on this part, when you have any b with power of x, you will write those equations, the original equations, and then add L and B. But now it's not x, but sine, which means you are going to use the chain rule property. So we have the outside function, which is the this b with power of x, and an inside function, which is the sine x. Okay, this is one of my exam questions. I think 2 years ago. Okay, so as long as you practice outside function, outside function, inside function, and you keep consistency, you're keeping your consistency, I think you will be familiar. You will be familiar with this. Okay. Okay. So outside function. This is outside functions. Outside. Well, we can write. Let me write just b with power of x. Okay, just to make notes. And then inside is this. Or we could say 5 with power of x, and then we put sine inside this 5 with power of x. So we change the x with sine x. Okay. Now slowly we could see that if we have this, okay, we have this. So what we need to do is we write the whole thing, okay, the original equation. So we could write the whole thing here, 5 with power sine x, and then adding L and 5, and then multiply with, let me write the dx of sine x. So we could have 5 sine x, L and 5, and then cosine x. Okay, so as long as you keep consistency, outside function, inside function, any functions that seems complicated, you can try to work out slowly, slowly, but actually you will get the results. You will get the results. Okay. Okay, we will have a break, so okay, we will continue after the break. Okay. Uh, okay. 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 Just to give you summary what we did in the chain rule. Let me give you like really a lot of functions inside the function inside the function. So we start with k is the most inside, right? And then h. So it's like a cutting onion. You have layer, layer, layer. Okay. So the inner one, the inner layer is the k, and then outside is h, and then more outside is g, and then the outside one is f. Okay. So the way we think how to write this in terms of the derivatives is first is we take the outside function. So the most outside one is f, right? So we could take f as, let's just write like f prime as usual and write all the things here. So you're taking slowly, slowly like that, okay? And the next thing is take the dx, right in terms of just before it's derived. Okay, so we take this and then it's supposed to be the inside function. So the inside function is if f is outside, then the inside start with g. So let's start with g. Okay, let's start with g, and then h, and then k. Okay, and if you look on this blue color here, we have another chain rule. Okay, so we can start to write this again, g prime here. So f prime blah blah blah, g prime blah blah blah, and then the inside functions h. So we are going to have a like really long chain rule. Okay, but this is just to show you that no matter how many functions you have, we can always take them as a chain. Okay, as long as we are consistent writing the outside functions and then inside functions. Okay, and then you can write this. Maybe let me just take this. So write really long here, but let me just take times to write, just to give you an idea that we can solve this. And then we can write the g prime and then take ddx of the inside functions h. Okay. And then again we can still write really long, but this is just to give you an idea how we can solve this. And then yeah, I think we can end with k prime x. Okay. Okay, so this is giving you an idea how we can solve many layers of the functions. Okay, if you have a composite function that has many layers, we could still solve that. Okay, so I would not stop just taking f prime g prime x. Okay, we can do a lot. Okay, with those knowledge, I think. Okay, I will stop the chain rule up until here. We are going to have, I think, several examples tomorrow, more practice. I will give you examples regarding to what we have learned. Okay. So next is the implicit differentiation. So the word implicit, okay, uh, is not really. If you can see, like physically, you can see. We say okay, it's explicit, but implicit means that we know, but it's not really clear to be seen. Okay, that's implicit means. So, what does it mean for differentiation? Now, we can start with we learn. Okay, we learn. Let me write some words here. So far, we learn uh, functions expressed in y equal function of x. Okay, like for example, y equal square root of x, y equal x squared plus 3x plus 8 probably, or maybe the trigonometric sine x. We learn all the functions, they have only one variable here, right? Function of one variable, single variable x. Okay. Now the implicit here is if we have another variable inside this expressions in which the variable is actually our y. For example, if we take consider let's say we consider the circle equations. Okay? X squared plus y squared equal 25. Oh, it's squared, sorry. Okay. So we know that this is a circle equation with radius phi, right? But can we differentiate this? Can we differentiate this? Okay. Because we have y. Before we have only one variable explicitly in the functions, but now we have y, which y is function of x. So how do we able to solve this? How do we differentiate? First method, we can take the y squared. We can take the y squared here, and we can take this. We can take these equations. So we can have the positive. So you will have a circle, but you will need to define the circle, and the one is the top one, the positive, and the negative will be the bottom one. Okay, if you have the circle. And you can derive this y, right? Because you have the square root here as this chain rule. Square root, so you have 1 over blah 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 here, and then multiply with negative 2x, right? That's one way. But is there any any simple way that we can differentiate directly from here? Okay. Let me give you the techniques first and maybe explanations after that. Okay. Remember that y is function of x. So if you want to derive and take the f prime, so we have dy over dx is f prime x, right? Okay, so that's the first thing. So if we have x squared plus y squared equal 25, so if we want to differentiate this, okay, remember that we are looking at the perspective that the independent variable is x, and y is our dependent variable, which is y equal function of x. Okay, so the idea is we treat the x squared as usual, differentiate with respect to x. So x squared becomes 2x. Okay, not a problem there. And y squared. Remember that if you have y, if you want to take the derivative, it becomes dy over dx, because y is having this implicitly. They are having the x inside. So we are taking y as x, but we need to add something at the end. Okay, so x squared becomes 2x. Y squared, if you take this as x, this will be 2y, right? So we write 2y. But according to the chain rule, we need to multiply this with something that makes it more logical, more makes sense. So we need to take this dy over dx to here. Okay. And 25 is constant, so it's 0. Okay. So basically, implicit differentiation is just taking y, treat y similarly as x, but adding with something. Because y is function of x, so we need to add this dy over dx. Okay. If we take x and y as a different variable, they both independent, it will be on calculus 2. Okay. So calculus 1, we are focused on single variable or single independent variable, which usually we take x. But y here is not really other variable. This y is actually we treat as a function of x. Okay. Okay. So implicit differentiations is maybe right here. So differentially or differentiating uh, both sides. Let me write with respect to x and solving equation for dy over dx. So what does it mean? It means that our solutions that we were, or our goal, if we want to, what is the first derivative of this? The first derivative means we are going to find this dy over dx. And this dy over dx, it will implicitly appear in the equation. Implicitly appear. That's how it means, the implicit differentiation. So the next thing we need to do is we are going to solve this dy over dx. Okay? So solving that will give you dy over dx negative x over y. So this will be the result. Okay. Okay. So how the implicit means, okay, that the dy over dx will implicitly appear when you try to take this derivative. Okay. So if the question is what's the derivative of this, then this will be your answer. Okay. Mm-hmm. From here, solve this. Okay. 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 Maybe you're right. Maybe give some explanation here. Need to resize a little bit. Maybe here. And then, okay. Okay, I hope it's clear. Okay. So implicit differentiation, we start by looking at the equations. Usually they will have some x and y inside. And remember y is a function of x. Then we could treat the equations just like normal derivatives, just like normal derivatives. So x squared becomes 2x. Y squared we treat like x, but we multiply with dy over dx at the end. So y squared becomes 2y, and then multiply with dy dx. Okay. So every time you see y, you need to add dy over dx at the end. Okay. So imagine that if we have a long equation, maybe it has some y, then you need to group dy over dx at the end, and then solve the dy over dx. Okay. So at least two process derive as usual, but adding dy over dx on y. After that, solving the dy over dx. Okay. Okay. Yes. The up one. Oh yeah. Okay, your textbook has some examples. Let me explain that first, and we can try to solve together. I think this implicit techniques is uh, probably one technique that's useful um, for your probably if you take more courses related to mathematics. I think they will also still and in unit calculus. I think this implicit will be very good techniques. Very good techniques. Okay, let me give you example. Okay, maybe example as state in your textbook. Sine x plus y. So we could start slowly, taking times, and we see that we have y inside this equations. We have y in this sign x plus y, and y squared. Okay, and treat this equations. If you are maybe not really sure on y, you can take y just as x, okay? Just as x or any variable. And according to the chain rule, I think we can solve this. Remember, this is the outside functions, so we can take this as cosine and x plus y, and then multiply with the inside functions, derive 1 plus y becomes dy over dx. Okay, that's the left part. The right equations, we're going to look this as a product rule. Okay, we are having fg, right? Fg, so f prime g plus g prime f. Okay, so now I think from the chain rule, implicit one, we are going to see more and more complicated equations as you follow. So I hope I can give you the every week some additional exercises, and you can also practice those exercises individually. Okay, I hope. And maybe sometimes I'm giving you homework. Sometimes maybe the next homework, maybe next week. Okay, not this week. This week maybe focus on quiz. Okay, quiz, the limit quiz. Okay. So first is, let me copy this. Copy here and take the derivative. So this will be cosine x plus y. Let me write slowly here for each step. This is x plus y. And this part here is fg. So we will have d dx of y squared and then multiply cos x plus y squared multiply d dx. So cosine, and this will be 1 plus dy over dx. It takes time because it has a long equation. So you need to be focused, consistent. Okay, take times. Don't worry. Don't rush yourself. Take slowly. Take slowly. This will be 2y dy over dx, or maybe let me write dy over dx at the end. This will be cosine x here, and then plus. Uh, Cosine is negative, so I think it should be negative here. And then we need to solve slowly. So this will be, let me multiply this, multiply cos x plus y plus cos x plus y, and then dy over dx. Okay, and then combine the dy over dx together. So let me combine together. So dy over dx cos x plus y and minus 2y cosine x. This will be minus y squared sine x and then minus cosine x plus y. And dy over dx is equal, it's quite long here, negative y squared sine x minus cosine x plus y over cosine x plus y minus 2y cosine x. If this is too small from behind, too small, or you can still see, it's okay. Okay, this is if the question is asking the first derivative. Okay. If you have given the same equation, but it's asking the second derivative, well, this is your first derivative, and then you need to to rewrite this and then make it the second derivative, and you can do the quotient rule. But I think it's going to be messy, so I will not use this one. It's going to be really bad. Still doable, but yeah, it's really messy. Imagine that you will need to square this and then take the derivative of this minus take derivative this, multiply this, minus derivative this, multiply this. But it could be a question in the implicit. It could be like you have an equation and the equation is asking second derivative. But the way you process the question is you need to take the first derivative, like making this dy over dx is equal this, and then derive one more time. Okay. I think the next example I will going to give that the second derivative one, but I think more human, more human, more reasonable in the process. Okay. And let me give you on the right side here, so you can still write notes. The example. So if x power of 4 plus y power of 4 is equal 16. Question is the y prime and y double prime, which means it's the first derivative, the second derivative. Try first, okay? Try first. I just want to let you be familiar with the process, with the techniques, okay? The equation is x with power of 4 plus y power of 4 equals 16. I think the first derivative should be not really complicated. You will have the cube from the power of 4, right? and you will get dy over dx from y, and solve dy over dx. You get the at least the equation for the y prime. Okay. And to get the y double prime, we need to derive the y prime. Okay, derive the y prime. So, for example, if the question is asking just this y double prime, you still need to write down the y prime. Okay, that's the process. Okay, okay, good. Yeah, and then one more to derive. Yeah, take slowly. Yes, okay. One more time. The second derivative. So I think for the first derivative, things should be okay. So you have the x power 4, y power 4 equals 16. Take the derivative. And we are doing implicitly. So we are going to have 4x cubed plus 4y cubed, and then add dy over dx at the end, and then equals 0. So dy over dx is going to be negative x cubed divided by y cubed. Or this is y prime, okay, matching the terms. So this second derivative, or this the double prime, this going to be, let me write one by one the process, d dx of the equation here. Okay. So we take this using the quotient rule. So this is f, this is g. So the g will have squared on the bottom side, and this will be negative. Or maybe let me take the negative maybe outside. Take negative here, so I will focus the positive first. So 3x squared, and then y cubed minus the x cubed, and then 3y squared, and then dy over dx. Or if you want to write y prime, that's okay. Y prime, that's okay. So you will see that we have another dy over dx, which means we are going to substitute here, going here. Okay, we substitute dy over dx because we have the form here. Okay, okay, that's the idea. Then we can finish off by taking this negative 3x squared y cubed this is y with power of 6. So it will cancel the, so this will be plus over y. So this will be 3x squared y cubed plus 3x cubed or x power of 6 over y. But we can take y over here and making this cube with power of 4 and then divide by y power of 6. So we will have negative 3x squared y, or maybe taking 3 outside, x squared y 4 plus x power 6, or maybe taking x squared also. And then x power of 4, and then divide by y with power of 7. And then remember, this y power of 4 and x power of 4 is 16, right? 16 from the equation, original equation. So we could change also this into 16. So we'll have negative 48 x squared over y power of 7. So that is the second derivative. Okay, any questions? Any questions? Any questions? Yeah, it seems complicated on the second part here. But actually in implicit, when we try to derive second time, we we are pretty sure that somewhere in between the process we are going to get the dy over dx. Okay, and the key to solve this is to substitute this to what we have before. Okay, the first derivative. Okay, and then sometimes at the end you will see it seems that we get the original equation, okay, that stated at the beginning. Okay, to make it familiar, let me give you one question, but we can solve tomorrow, but you can solve if you want to try at home. Uh, find y double prime from okay, these questions, I don't think we can solve by today because you see this is y double prime, so it's supposed to be similar with this. So I would like you to try, and we can see tomorrow the solution. Okay, any questions? Any questions? Is it too complicated? Is it? It's not. Oh, a few, no? Is it complicated? I think so. So. Yeah, I think it's in between. the key is finding consistency. Finding consistency. Consistent, and then familiar with the algebra. That will be helpful because sometimes you can simplify the process through some algebraic forms. You can rewrite the forms. Before this one, I think this is belongs to how good your techniques is and how good your algebra is. Okay. And there will be one not like for example this case we simply solved by the implicit differentiation. But maybe after we learn more in the future, we can see that maybe this is not only the one method. We can find another method, and in the future you can choose which method you prefer. Okay. Okay. After this, I'm going to give you another feedback question. I think I'm only preparing. I think 2 questions. Um, it's about the last week um, derivatives. So hopefully you still can remember what it is. And yeah, okay. Okay, any questions here? If no, I will move to the feedback and maybe wait for some time if you want to write this. You still write this equation. Yeah. That's already a good way to go. Okay, and then we can start our feedbacks. Okay, are you ready? Have you scanned the QR code? Or if you difficult to scan, you can go to the website. Okay, I think you're ready. Okay. Okay, we can start. Okay, remember, write your student ID so I can assign you for a bonus point. You don't need to win the game to get the bonus point. Okay, there will be like several scoring systems. Okay, as long as you join in, you already get the point. Okay, let's start. Okay, compute the product rule dft prime fine. Yeah, perhaps it's too fast. 1 minute and a half, but I think the number should be okay. So you're just solving the numbers. And remember the product rule. Okay, the product rule. So if you have fg prime, what will be the product rule? Okay. If you have minus, don't write space between the sign and the number. Okay. So I already give you a clue what the answer will be. Okay, so 40 seconds left. Yeah, 20 seconds. Okay. Okay, good. Okay. Okay, okay. Okay, very tight. Okay. Okay, get ready for the next one. Okay, get ready. It's a little bit difficult, but I hope you can get it. So 4 minutes. 4 minutes. Okay, let me give you a clue. Differentiable everywhere means you need to differentiate from the left and the right. Need to be the same. Okay, need to be the same. And the key is this x equal 2. That will be the key. Okay. So remember using the limit from the left or the right. And then you can go directly to derivative to differentiate. The differentiate from the left equal differentiate from the right. That's the key. It's okay if you feel it's too difficult. We'll give you solutions tomorrow. Okay, this one. First is you need to differentiate both equations. Okay. Why we need to differentiate this? Because we need to know that if this is differentiable everywhere, then we can differentiate all of them. All of the equation we can differentiate. And then this x equal to, like the limit problem, is our important point. Which means that we are going to look at this point, because from this point, the equations will be different. After if less than 2, this is the equation. If greater than 2, mx plus b is the equation. If you differentiate these two, at least you get 2x, and then this b is just a constant, so we can just take it 0. So we know the m from that point. From x equal to, we know the m. And then later part, you will know how to get b. That's the clue. I hope it's enough, sufficient. This is just f multiplied b. Okay, after you check the differentiation, check continuity. The second part. That's how you get B. Okay. I will explain tomorrow with another example. Because I think this is a typical question in the exam. This is difficult. I need to more practice. Okay, I think most of you get the correct answer. Okay. Oh, we'll see who. Oh, okay. Who is that? Congratulations. Okay. So last part, as usual, student ID, and if you have any feedback, or maybe you want to have more exercise, I'm trying every week giving you video solutions, so hopefully it can help. So maybe the next video solution, maybe next week. This week we will focus on your quiz limit. Okay, if you finish, then we'll end the class today. Yes.
Ini kan tadi ini dari semuanya ini gimana? Dicoret sama ini minyak dicoret.
Enggak, Y-nya disamain ke sini. Makanya Y pangkat 3 jadi pangkat 4, Y-nya per Y gitu.